Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground, beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering, but also of ambition, and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension, as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions in particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics, literally. By analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limit of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey did not end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called Alpha has successfully trapped anti-hydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang Theory suggests there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, a fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but also pushes the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider from a chain of small gas petals. Each proton began its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas petals, gaining energy at each stage until they finally arrive at LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, that energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well focused. The beams are carefully regulated or squeezed to ensure they collide in the detector at the point where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron volts at even higher luminosities than before, meaning more collisions for data-gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2202 mega-electron volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they have studied the behavior of the neutral D meson and neutral strange B meson, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomenon's been captured with unprecedented precision in recent datasets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into quark-gluon plasma. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the standard model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. Now, while the LHC can create tiny black holes, they are on the quantum scale and evaporate almost instantaneously through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. And finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multidimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. The ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our three-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions at the LHC where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It is planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications to go far beyond particle physics, promising a glimpse into the very fabric of the cosmos and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time.